Yeah, exactly. And you put it into a multi-million-dollar fMRI machine, and you ask it to identify human emotions. And and here's the crazy part. The machine actually spits out a scan telling you the fish is thinking.
It honestly sounds like the setup to a surreal joke.
Mm.
But it is, one of the most famous cautionary tales in modern neuroscience.
Which makes it the absolute perfect starting point for our deep dive today, because today we are exploring a massive challenge.
Oh, definitely.
We're looking at how to anchor complex, invisible systems into grounded physical reality, like whether you're looking at an fMRI scan or the output of some cutting-edge AI algorithm, what actually happens when our most trusted tools start seeing things that, well, completely defy the laws of physics.
And to answer that, we're pulling from a really fascinating stack of sources that, on the surface, might seem totally unrelated.
Right. We've got an academic strategy from an AI notebook competition, some real-world field data from an urban butterfly sanctuary in New York, and this is my favorite, a 60 million year evolutionary chronicle.
It's a brilliant mix of materials, really, because by tracing the line through all three, we can build this comprehensive understanding of why our digital systems are currently so fragile and, how we can look to ancient biological systems to actually fix them.
So for you listening, whether you're prepping for a big tech meeting or you're just, I don't know, trying to navigate a world completely flooded with AI-generated content, I promise that by the end of this deep dive, you're going to have a totally new mental model.
A completely new way of seeing things.
Exactly. A model for understanding how AI thinks, how nature self-regulates, and how those two things are actually profoundly connected. So let's go back to that dead Atlantic salmon.
The 2009 study, right?
Yeah, back in 2009, researchers put this lifeless fish in a scanner, and they showed it photographs of humans in different social situations. They ran the standard statistical analysis pipelines they used at the time, and the software literally lit up with brain activity.
Yeah, the software confidently reported that the dead salmon had brain regions actively predicting social emotions, which is wild.
Wait, so the machine was convinced the fish was empathizing?
Pretty much. But, this wasn't evidence of supernatural fish cognition. It was actually a massive failure to correct for multiple statistical comparisons.
Right, the math was just wrong.
Well, the math lacked guardrails. If you feed enough random noise into a highly sensitive algorithm without the right mathematical boundaries, it will eventually find a pattern that looks exactly like a real signal.
It's like playing connect the dots on a page filled with random static.
Oh, that's a great way to put it.
Like if you draw enough lines, you will eventually draw a shape that looks like a house, but it definitely doesn't mean a house was actually there in the first place.
That is the perfect analogy. And fast forward to today, we are seeing this exact same dead salmon problem erupting in artificial intelligence.
Which is terrifying.
It really is. We have a recent paper in our sources that exposes how modern AI interpretability tools, these are the specific programs designed to tell us why an AI made a certain decision, are actually suffering from this exact same illusion.
Okay, let's unpack this a little bit, because the sources mention tools like saliency maps and GradCam. And for anyone who doesn't spend their day, training neural networks, a saliency map is basically a heat map, right?
Essentially, yes.
It just highlights the exact pixels in an image that made the AI decide, for instance, a picture was a dog instead of a cat.
That is the intention behind them, absolutely.
Yeah.
But the researchers in this paper did something completely devious.
Oh, I love this part.
They took a neural network and they completely randomized its internal weights.
Meaning they scrambled its brain?
Exactly. They gave the AI zero actual knowledge. They turned its processing into pure, unadulterated noise. And then they asked those interpretability tools to explain the AI's decisions.
And the tools still spit out plausible-looking heat maps, right?
Yeah.
They just hallucinated an explanation out of thin air.
They did. And this points to a fundamental statistical flaw called non-identifiability.
Non-identifiability, okay.
Yeah. These tools are just finding highly contrasted pixel patterns and, attributing deep meaning to them, even when there's absolutely zero physical logic behind the pattern. They're just drawing your house in the static.
Which is, when you think about the real-world applications of this, it's pretty scary.
Oh, it's a huge vulnerability.
Take deepfake forensics, for example. If someone makes a deepfake of your face or your voice to try and scam your family, you want the AI security systems to be foolproof. But if those security systems are easily fooled by random pixel noise, we're in big trouble.
Let's walk through a really concrete example of that. Imagine a deepfake video of someone writing a handwritten letter. The standard AI interpretability tool might scan that video, highlight some completely arbitrary pixel weight anomalies in the background.
Like a digital dead salmon.
Exactly. And it confidently declares the video is fake based on that noise. But it completely misses the glaring physical impossibility happening in the foreground.
Like what?
Like the fact that the person's pen trajectory in the video doesn't actually match the text appearing on the paper.
Oh, wow. So it completely misses the obvious physics because it's just staring at pixel math.
Precisely. It doesn't understand the physical world.
Okay, but I want to push back here a little bit.
Sure.
Isn't pixel data literally all a computer vision model has? I mean, how can we possibly expect an AI, which lives entirely in a box of code, to understand the physics of a pen on paper? Doesn't teaching an AI the laws of physics require just an unimaginable amount of computing power?
You're hitting on the core debate in AI right now.
Mm-hmm.
Relying on statistical shortcuts is cheap, right?
Uh-huh.
It's computationally easy. Simulating actual physics is incredibly expensive. But if we only train AI on statistical pixel patterns, it'll only ever understand statistical pixel patterns.
It'll just keep seeing dead salmons.
Exactly. So to solve this, researchers are arguing that true visual veracity requires what they call code world models. We need to build a retrodictive layer into the AI.
A retrodictive layer. Help me out with that term, because the paper defines it as assessing the actual physical state logic, which, I mean, just sounds like trading one piece of jargon for another.
Fair enough. Let's use a much simpler analogy. Retrodictive basically means reverse engineering reality.
Okay.
If you walk outside and you see a puddle on the sidewalk, retrodictive logic tells you it probably rained.
Right, because puddles come from rain.
You didn't actually see the rain, but you reverse engineer the cause from the physical evidence. The AI needs to be able to look at the text on a page and reverse engineer if the human hand in the video actually made the specific physical movements required to write it.
So instead of just asking the AI, does this arrangement of pixels look statistically familiar, we're forcing the AI to ask, does this image make logical sense in the physical world?
Yes, it's a huge shift. Shifting from pixel statistics to grounded truth.
Grounded truth. I like that.
Grounded truth is the key to all of this.
Yeah.
But to build these code world models, you need a test bed. You need an environment where the physical reality is complex, it's measurable, and it's entirely unforgiving of statistical hallucinations.
Which brings us to the dirt.
Yes, nature.
Because what better, messier test bed is there than raw nature? Which leads us directly to the fascinating AlphaXIF and Marimo notebook competition submission in our sources.
The VITA-VQ-M project.
Right, which stands for, let me get this right, Visual Integrity Truth Algorithm Veracity Quotient Mapping.
It is definitely an imposing acronym.
Just a bit.
But the execution of it is incredibly elegant. It takes this highly theoretical AI problem, the fragility of computer vision, and it shifts it entirely out of lab and into an urban butterfly sanctuary in New York City.
The Inwood Butterfly Sanctuary. And the founder, Keith De Cesare, is dealing with an ecological reality that's just a perfect microcosm of human intervention.
It really is.
Because New York State actually has legislation, the Monarch Preservation Plan, mandating the conservation of native milkweed, which, is the only plant monarch caterpillars can actually eat.
Right. Without it, they die.
Exactly. But despite the laws, municipal maintenance crews frequently just eradicate the milkweed anyway because they see it as weeds.
It really, highlights that classic disconnect between high-level policy and what's actually happening on the ground. But the sanctuary pushes back through localized community action.
Right, using protective enclosures and targeted propagation.
Yes, and according to the field data, they have actually managed to raise the survival rate of monarch caterpillars from under 2% in the wild to an astonishing 98%.
That is just an incredible jump, but I am a bit confused on the mechanics here, to be honest.
Oh.
Well, I get that they are using the sanctuary to test the VITA AI framework, but how does a community member just taking a smartphone photo of a butterfly plant actually tell an AI about complex ecological variables? Like,
Right.
The sources mention that AI calculates parasite load and predator pressure.
Right.
Are these people, out there taking macro shots of tiny stink bugs?
It's a great question, and it goes right back to that retrodictive logic we discussed earlier.
Yeah.
The AI isn't necessarily looking for an individual wasp or ant in the photo.
Oh, it's not.
No. Users take raw field photos of the milkweed plants, and the smartphone embeds GPS provenance metadata. The AI then analyzes the broader visual context.
Like what kind of context?
It looks at specific stippling patterns on the leaves, the type of chew marks on the edges,
Mm.
the overall discoloration of the plant, and it correlates all of that with the geographic location.
Oh, wow.
So it reverse engineers the presence of predators and parasites based on the physical damage they leave behind.
Ah, so it's looking at the puddles to figure out if it rained. So instead of the rigid mathematical formula we usually see in academic papers, it's essentially calculating a dynamic survival score. The math basically says the AI estimates the baseline capacity, like how much food is actually available, and then it mathematically penalizes that score based on the visible signs of threats.
That is the core causal equation at work there. It takes the milkweed coverage, factors in the predators and parasites, and it outputs the predicted monarch density.
That's amazing.
And the researchers built this interactive user interface, they call it an ecological varigraph, powered by a tool called Microfy, inside their Marimo notebook. Lets users interactively slide these ecological vectors around.
Okay, so you could say slide the milkweed coverage from 40% up to 80% and instantly see the predicted monarch density skyrocket.
Precisely.
Yeah.
And crucially, it provides statistical bootstrap uncertainty bands alongside those predictions.
Okay, let's do a quick translation for the listener there. A bootstrap uncertainty band is basically the AI's way of saying, I think the survival rate is 80%, but based on the fuzziness of this particular photo, it could be anywhere from 70 to 90.
That's it exactly.
He gives you a confidence interval, allowing the AI to admit when it isn't entirely sure.
Which is a massive scientific breakthrough for AI interpretability.
Really? Why is that so big?
Because by explicitly testing the AI's vision against measurable ecological ground truth, the actual observable survival of these real monarchs, we completely solve that non-identifiability problem.
Oh, I see.
We turn a theoretical critique about AI hallucination into actionable science. If the AI hallucinates a dead salmon in this scenario, it is immediately caught, because its prediction simply won't align with the physical reality of the sanctuary.
It essentially forces the algorithm to answer to the dirt.
Yes, beautifully put.
But what really struck me in the notes is that Keith didn't just stop at building an AI tool for researchers. He recognized that if you want to protect the ecosystem long term, you really have to cultivate empathy alongside the data.
That's the human element.
Right, which is why he took this technology out of the sanctuary and brought it into an elementary school.
Yeah, he integrated it into a K-5 curriculum called Bridging Tomorrow, which is being piloted at school in the Square in New York City.
And to get kids to actually comprehend these complex systems, he pairs the AI data with storytelling. He introduces them to Pip.
Pip, yes. Pip is the educational stand-in for a real creature called Myaces.
Myaces.
Yeah, this was a generalized tree-dwelling ancestor from the Eocene era, roughly 60 million years ago. Pip is essentially the single stem on the evolutionary tree that eventually blossoms into all modern carnivores.
And the curriculum traces this lineage through a massive climate shift, right? A global cooling event they call the Great Divergence at the River of Life.
Right. The environment changed drastically, and Pip's descendants had to adapt. They basically split into two completely different survival algorithms.
And it's fascinating how distinct those two paths become. The first path led to the families.
The Canids?
Right, the ancestors of modern wolves. Driven by the expanding open plains, they evolved for speed and endurance. But speed wasn't enough. They had to invent complex social structures.
They evolved communication, territorial boundaries, and highly strategic cooperative hunting.
And their entire survival strategy was based on managing herd density. They instinctively target the sick and the weak animals, which actually protects the wider ecosystem from overgrazing and disease.
And then you have the second path, which led to the loners.
The bears.
The Ursins, exactly. They stayed in the cooling forests. Instead of speed, they evolved sheer mass. Instead of social packs, they embraced absolute solitude. And to survive the brutal winters, they evolved the incredible metabolic machinery for hibernation.
And here's where it gets really interesting to me. The curriculum dives into their feeding habits, specifically with salmon.
Oh, this is such a great detail.
A bear will catch a salmon, eat only the fattiest, most calorically dense parts, like the brains, the eggs, the belly, and just leave the rest of the carcass sitting on the riverbank. On the surface, that looks incredibly wasteful.
It does. But ecologically, it's brilliant. That discarded carcass acts as a nutrient subsidy. It fertilizes the soil on the riverbank, which grows the trees, which eventually produce the berries the bear will need to eat to survive the following year.
Notice the narrative loop there. We started the deep dive with a dead salmon in a lab that broke an algorithm, and now we have a dead salmon in a forest that perfectly sustains one.
It's incredible.
The wolves are basically nature's park rangers managing the population, and the bears are nature's farmers fertilizing the soil. They were executing perfect ecological algorithms millions of years before humans ever invented computer code.
And the curriculum actually has a term for this. It calls it intrinsic ecological wisdom, or IUW.
IUW.
Yeah. It's this profound concept that these apex predators evolved entirely selfish survival instincts that unintentionally, but perfectly, act as self-regulating mechanisms for their entire ecosystems. Their biology is a code world model, refined over 60 million years of trial and error.
So what does this all mean when we connect Pip the bear back to our fragile AI tools and our monarch butterflies?
Well, if we zoom out to the bigger picture, it highlights a really urgent shift. For 60 million years, evolution was governed by the intrinsic control of these apex predators.
Yeah.
The environment self-regulated.
Right.
But today, the primary threats to these ecosystems are extrinsic. They're human-made.
Yeah, a wolf's pack boundary instinct cannot negotiate with a logging company.
Exactly.
A bear's hibernation cycle can't adapt to rapid climate change. And a monarch butterfly's migratory instinct absolutely cannot survive a municipal lawnmower destroying its only food source.
And animals' intrinsic ecological wisdom cannot fight a highway. Because the threats are now extrinsic, the regulation must become extrinsic.
We have to step up.
Yes. Humans have to use our tools, like the VITA AI framework, to become the extrinsic regulators. We have to trade our short-term extraction for long-term ecological harmony.
We basically have to build our own intrinsic ecological wisdom into the tools we create.
Exactly.
Wow. Okay, let's take a breath and look at the massive journey we just went on today.
It's been quite a ride.
We started with the statistical illusion of a dead salmon in an MRI machine, which showed us how easily ungrounded systems can just hallucinate false signals.
Then we explored how to actually fix those hallucinations by grounding AI algorithms in the real-world dirt of an urban butterfly sanctuary.
Right. We saw that technology is only as robust as the physical reality it measures, using that retrodictive logic to ensure our digital models actually understand physical laws.
And finally, we looked at how K-5 students are learning from the 60 million year evolution of wolves and bears.
Which is amazing.
We saw that true intelligence, whether it's artificial or biological, is fundamentally about self-regulation and empathy. It's about understanding your localized place in a much wider system.
This raises an important question for you listening to this right now. Whether you're coding a complex neural network, analyzing data for a corporate strategy, or just, planting a garden in your backyard, the tool itself, the algorithm, the spreadsheet, the shovel matters far less than the intention behind it.
Oh, absolutely.
We have an obligation to design and use systems that actually understand, respect, and sustain the broader physical world they operate in. We can't just stare at the pixels and hope the static turns into a house.
We have to look at the whole picture.
So to leave you with a final thought to ponder today, think about the butterflies in your own world. As our AI tools grow exponentially more powerful and our daily lives get faster, what small, localized, overlooked systems around you could have a massive rippling impact if you just gave them the right space and attention?
It's a great question to ask.
Maybe the key to surviving our digital future isn't floating up in the cloud at all. Maybe it's about making sure we don't end up blindly trusting a dead salmon when there's a living, breathing ecosystem waiting for us right outside our window.